Hi, I'm Ben-Yaakov. This presentation is entitled A Primer to Varistors. There is a disclaimer here. Please note that the devices shown in this presentation are shown for educational purposes only. There is no endorsement or recommendation implied here, and I'm not affiliated with any of the manufacturers that are mentioned in this presentation, and that other vendors are offering devices with similar functionality. So what's the need for Varistor? It's a matter of protection. If we have a system like this, which is connected to a line, say, we have to protect it against overvoltage that could be due to the changes in the line, could be due to lighting, and there are many other reasons that the voltage can rise either momentarily or perhaps for certain extended time, and the system has to protect it. The needed protection level is to several kilovolts, and this is what the regulation called for. There are different regulations, UL and others, that specify the level of protection that you have to have and the disturbance that you have actually to test the system with. That is, you have to generate a voltage and to see whether the system is withstanding this disturbance. So the voltage could be to several kilovolts and the current to tens of kiloamps. So it's quite a bit of a requirement. Now, what are the units or the devices that we have? What's the arsenal here? We have Zener diodes, which are for low power, low current, and they are not very well suited for protection. There is the TVS, the transit voltage suppressor, which are sort of a beefed up Zener diode, and they are intended for higher current, not very high current, not in the kiloamp, but hundreds of amp maybe, and they are quite expensive when it comes to high power devices. And then we have the Varistor, which is relatively a less expensive device, and it can protect to very high voltages, very high current. So this is a very versatile element, very economical. And then we have the spark gap, which perhaps is one of the first one to have been in as far as the historical development of protectors. It's basically two electrodes, could be either in air or preferably in a controlled atmosphere, and it breaks down when the voltage is just too high. Actually, it makes a short here. So one has to take into account that this is becoming a short, and one has to avoid a sustained short, of course. Now, the varistors, which are the subject matter of this presentation, actually come in two types. There is the silicon carbide, which is a very robust device made of silicon carbide particles, and it can withstand very high voltages, very high current. High voltage is obtained by stacking a number of units in series. The problem with the silicon carbide is that the knee is very soft. This is the voltage and this is the current. You like it to be like a Zener, very, very sharp. And the silicon carbide is soft, and primarily here there is a problem because it sort of starts up to rise early, and therefore the leakage current in the region that you work is fairly high. So therefore they are not used that much anymore unless for very, very high power units. But even there is a tendency to change and use the zinc oxide type varistor or metal oxide varistor, the move as it is called, because it has a much sharper knee, so the leakage here is much lower, and therefore the power dissipation here, you don't have to protect it that much. But then there is a problem here, which we'll discuss in this presentation, and that is the degradation of the unit when it is exposed to a number of pulses or high surges. It'll degrade, could actually start a flame, burn out. So one has actually to protect the unit against overheating, and we'll talk about it a little bit later. Now, there is a misconception usually that if you have a voltage source, a spike here, you put a varistor and then it'll clamp it. Well, this is not the case, because if this is the situation and this is a voltage source, then the current will be extremely high, and what will be happening is actually this varistor will be destroyed because there is no limit to the current here. In reality, we are talking about a situation in which there is an impedance, so there is a voltage divider here. Here, the voltage is clamped, and here, this impedance is actually limiting the current. This could be an inherent parasitic impedance of, say, the line, the resistance, the inductance, or it could be something that we are putting in purpose in order to form this voltage divider. So any protection unit is actually relying on a voltage divider, not just clamping it, but it's actually dividing the voltage. There is always a series element that is controlling the current. In fact, the way to test the protection according to the regulation is to have a voltage source in series with an internal resistance, which is limiting the current to whatever given value is required by the regulation. So this could be a parasitic element or an added element that we have to have in order to get the voltage divider. So here is an example of maybe an excessive, but just an example of a front end that is very well protected. I'm not showing fuses, and also I'm not showing thermal cutoff, which are important, and I'll talk about them later on. We see here the spark gaps that will sort of the front end protection against lightning. Then we have varistors in between the line and neutral, and then in between the line and ground. This is just an EMI filter, and then we have here the varistor, which is protecting this side, and it has nicely this impedance as the attenuation. So this is a very good protection here. And then finally we can have a TVS, the output, say, of a rectifier against spikes of high voltage. So this is just an illustration of the use of these devices. Now here's a unit which is actually a commercial unit by a lighting and search company. This is a device you buy in order to protect, say, a washing machine or another equipment. It has the spark gap. There is an added impedance here for the varistor. It's a move. And then there is a TVS also at the end here for the equipment itself at the last resort for residual spikes. It's a two-channel unit. So what are the characteristics of a varistor? A varistor is a nonlinear resistor, and the relationship between the voltage and the current can be expressed either, say, this is more conventional, I is kV to the power of alpha, or V is some other constant times I to the power of beta, where of course alpha and beta are one over the other. So if in this particular case Vishay is preferring the beta, so this is the expression, V is I to the power of beta. So what we see here, that of course in a fixed resistor beta is 1, because this is like Ohm's law. And then we see here the resistance, this will be this resistance, it's linear. So this is now plotted in a log-log scale because we have a power here. And in the case of silicon carbide, you see that beta is 0.4. This is this beta. While in the case of zinc oxide, this is the MOV, it's a much lower, so therefore it will be sharper than this. And of course, an ideal varistor will be like a straight line. It will keep the voltage no matter what is the current. So this is of course just a theoretical notion. Now if we plot the VI characteristic of a practical varistor, and I'm talking about a zinc oxide or a MOV, and this is the log-log scale for the reason we just said. We see that the normal range, this is this range we are talking about, these lines are actually for this range. It's about a straight line, and the function is indeed this function, V is C I to the power of beta. But then we have another region here which is a more like a resistor here at the end. It's a nonlinearity here, and we call this the leakage range. This is below the operating point. That's the leakage point. So there is a very low current here. Of course, at the operating point, which is defined for a given leakage current. When a definition is given for the operator or normal operating point of a varistor, it always refers to a specific current. And 10 to the minus 3, that's 1 milliamp, is very, very typical of low voltage varistor. So this will be a varistor for 200 volt defined for 1 milliamp. And as the current increases due to clamping of the varistor, then the voltage will go up according to this line, according to this equation, until we come to a point that that's the end of the story. And in fact, at the very end, it's like a resistance, which is in the range of, say, 1 ohm, a very low resistance. But this is just beyond. This could be actually harming the varistor. This would be the normal operating region. In this particular case, we are talking about between the standby current of 1 milliamp to a current of 1 kiloamp, okay, 1000 amp. Another way to look at it is the family of, say, devices, commercial devices, which are shown here. Here is the 1 milliamp, and this is for various devices. This is for Burns company. And if I look now for a given unit, let's say this unit, which is about 180 volt, then I can see that at 10 amp, it is already about 280 volt here. That is, although the varistor is keeping the voltage, but one has to be aware that's not very, very constant. It's quite a variation. You see, this is only, relatively small current, as you'd expect from surges. It's only 10 amp, and it is already 280 volt. So that's quite a bit. And from this point, assuming that this is about a straight line, in the log-log scale, you can actually get out what is alpha, which will be, of course, from here, will be the log of I2 over I1, this is I2, I1, and log V2 of V1, or sometime, of course, shown as log I2 minus log I1, and same thing here for the denominator. So this is a very typical curve that you'll find in data sheets. Similar curves are shown here. This is actually limits. That's indeed the behavior, but this line, this is for a given device here, that's from another company, and what it shows here is the maximum leakage. This shows the maximum leakage boundary, and this shows the maximum clamping voltage boundary. So there is like a safety factor here and here, and this is why there is this jump. That's not the characteristic of the device, but rather the limits that the vendor is sort of promising for a given device. What about temperature effect? Now, the manufacturer are providing varistors that have a fairly stable operating point. Here's the operating point, like in this case it is again 1 milliamp. So as the temperature change, there is relatively small change in the current. But if you move to other lower value of current, you see that there is quite a bit of a change. So therefore, if you are at a given voltage here, it's a given voltage which is below, say, the nominal one, you'll see that as the temperature goes up, the leakage current is increasing. So leakage current is in fact increasing with temperature, and this in some situation can cause thermal runaway. That the higher the current, the higher the power dissipated, the temperature will go up, increase the current, so there could be a thermal runaway here. And there's the issue of degradation, which is a really severe issue of zinc oxide varistors. The main issue is the change in leakage. There is also a change in the ability to absorb energy. This, unfortunately, is not very well documented, and there's not much information about that. But about the change in leakage, there's quite a bit of information in the datasheet, and we'll go over it next. So first of all, how do we test varistors? The normal way to do it is provide a pulse. Normally it will be something of this shape, and there is a rise time. Here, say 8 microseconds, and then there is a time to 50% drop from the peak. And so when the pulse is specified as 8/20, it means that the rise time is 8 microseconds, and this duration here to 50% drop is 20 microseconds. And this is a very, very common pulse, test pulse for varistors. It is tested by a current pulse, which is generated, as I have said, by a voltage source with a limiting impedance resistor. And the currents we are talking about, the peak current, this is just in percent. The peak current are thousands and even higher kiloamp, depending on the device and the level of protection that you need. Now, again, the source for testing is the voltage plus a series resistor. So here is one example of how this degrading is specified. We see here a family of curves, and this is for limits for a number of repetitions that you have the pulse. Okay, so this first one is 1 pulse, and then 2 pulses, and then infinite number of pulses. This is during the lifetime of the varistor. That's not for one event, but something that is being accumulated over time. So let's look at the 1 pulse. What it means is that if there is a pulse of 100 microseconds, and the current is like 1500, 1500 amp here, then the unit will be damaged, but not more than 10% change in the normal voltage. That is, if this unit is specified, for example, for this 200 volt we talked about, then you would expect that the maximum change will be 10%, which is like from 200 volt, 20 volt. So it will be 180 volt for the same specified current, like 1 milliamp or whatever. Now, if, however, the pulse height is not that high, it's only, say, 15 amp, then it can go on indefinitely. I mean, here for 100 microseconds, go on, and it will damage it to this extent. And of course, below that, the unit will not be degraded. So this is one piece of information. The problem is, of course, that it's not that easy to predict the number of pulses that you'll have, the events of the surges that you might have. This can be relied on either some regulation or statistics of the region you are at. If you are in the region of very common lighting, then of course you can get some information about what is expected over a year and then take it into account. So what happens if the unit is degraded? When the unit is degraded, then obviously you'll have higher current passing through it. And as I've said, the higher current will cause a higher power dissipation, temperature rise, and eventually it could be a thermal runaway. So this could be the end result, which has 2 implications here, 2 problems. One, of course, the device is damaged, but then it can actually flame up and could burn, and it could actually be a dangerous fire event for the system. So this has to be avoided. But if you have a varistor and there are some events of surges and high current, then you might go into this situation. To solve this, vendors are providing thermal cutoff. Now this is a temperature sensitive element that acts like a fuse. It'll open up when the temperature goes up. Now it can come up with 2 ways, actually 3 ways. One is that it is an external element sitting nearby and sensing the temperature here, and then it'll cut off actually the varistor when the temperature is too high, that is in a case of a runaway. This could happen, by the way, if the line is high, and then obviously the current will start going up and temperature will go up, and again you'll have a runaway. Or it can be within the unit itself, okay? It could be within the unit itself, and in fact some companies like Littelfuse are offering a unit like this. So it looks like a varistor move, but it has inside the thermal fuse element, so that if the temperature goes up, it'll open, and then there'll be no current and there'll be no protection, okay? But it'll be a safety feature so that there'll be no flaming here due to the high temperature. Now, another element that they are offering is one which has an extra terminal here, which is from this point, and this point will be high voltage when the unit is operating, like here. It'll be here, it'll be high voltage if everything is okay, and there's a input voltage, and before, of course, the fuse is opening. And then you can have, say, a LED or some other electronic sensing device that will tell you that everything is okay. Now, if, of course, the temperature will go out, then there'll be no voltage here, so the LED will be off. So this is one way to protect the system against flaming. Now, what about the dynamic response? If we look at the equivalent circuit of a varistor, then what we have here is, first of all, the parasitic inductance, which is very, very low because this unit really has very low inductance to it. The capacitance, which is okay because actually it's also absorbing some of the energy and slowing the rise of the disturbance. This is the varistor itself. This is the way it is changing. This is some leakage, which is very high, so this really doesn't make any difference. And then we have, as we have said, the very, very high currents, residual ohmic resistance, which is very low, like 1 ohm. And here is an example that Littelfuse is providing. This is an original pulse here. And then here we have a unit which is clamping. The original pulse here is very fast. This is 500 picosecond per division. So it's a fairly fast rise time. This is the original circuit, and this is the clamping. You see that the response is very fast. And there is an overshoot, and there is some information about this overshoot. This is the pulse, of course. And what it says here, that if the pulse rise time is whatever, here, then with the given current, here are the currents now, this is the overshoot that you would expect, okay? So this is above the steady state or static VI curve, okay? So in 1,000 amp, say here it's a 0.4 microsecond, it'll be like 30% change, 130%. This is now above the clamping, and of course the reason why this is becoming higher at a faster rise time is because of the leakage. The leakage inductance is in fact the cause for the overshoot here, the peak that we see. So let's have a look now at some typical datasheet tables of a varistor. I've just picked at random one of the units. There's nothing special about it. These are disk type. There are many type of packaging that you can find these varistors, and sizes, of course. So this is just one example. So they have here two types, one coating by epoxy and one phenolic. They have different temperature and flaming features, so I'm not going into this. And then here is now the voltage for which this device, say this particular device, is intended. So this is intended for a voltage of 130 volt RMS or 170 DC. This would be like a US line So this is for this purpose. Here we have now the amount of energy that the unit can absorb without being distracted for one particular occurrence, for one surge, for one pulse. And this is limited by the amount of heat the device can store before the temperature goes up over the maximum allowable temperature for the device. So the energy, this is actually not watts, that is energy, that's joules. So, and this is for a test for a 2 millisecond current pulse. And of course, this value is the integral of V times I times this 2 milliseconds. And then the temperature rise will be this energy divided by the specific heat capacity of the material and the mass. So the larger the unit, of course, the larger the energy it can, the larger the size, the more energy it can store. This will be a unit with a larger size. Then we have the peak current, and this is for actual destruction. I mean, this is not for operating, but this is the highest one that the unit can tolerate. It might degrade after that, but it will not burn out, and there will be no catastrophic failure. So we are talking about 3.5 kiloamp here for one pulse, or if these are two pulses, then it specify how far apart they are supposed to be, is 2.5 kiloamp. And then we have the nominal voltage of the unit for 1 milliamp DC current. This is what I've said, this is how the unit is actually specified. So we see that it is between, let's go over here, between 184 and 225, and the difference is 41. So this is not a very accurate device. It is intended for, say, 170 volt protection, while the voltage here is could be on 180 or 224. But therefore, if the particular unit you have is 184, then the leakage will be high. While if the unit you have is 225 at 1 milliamp, then obviously the leakage at 170 will be much lower. So one has to take into account that these are not very accurate devices. The tolerances are quite a bit, but that's the way it goes. That's what we have. Then we have information about the clamping voltage. This is just an arbitrary current, 25 amp. It's a reasonable current that might occur in a system. And for this 25, the voltage will go up to 340. Okay, so this is based on the static curve, which goes to show that you see that the nominal is 170, and here with 25 amp is going to 340, so it's twice the value. And so one has to take into account that the varistor is not clamping to a very constant voltage, and as we have seen from the curve, the voltage is going up quite a bit. And finally, we have information about the capacitance, which is again not harming in fact, and we're talking about in the order of say 1 nanofarad or so. So what are the applications? There are many applications to a varistor, and I just copied some from publication of some companies. Here we see the input to a system. Here is to a line, and this will be like between the line and to ground. Could be to arrest the spikes of a relay connected to an inductive load. Without protection, of course, you'll have here spiking. That could damage, in fact, the contacts here. And then we can use it for over voltage protection of a transistor in case of say a relay. This could actually be put here also. And then they can be used for communication line. This is shown here for a LAN, the two lines of a LAN. And then here we have for USB also protection. So there are many applications, which obviously I cannot show all of them, and it's just a matter of the requirement of a system to be protected against a surge. Let me now finish up with an area which is kind of a little bit different from the regular power electronics, which is very high power systems. And I'm talking about the distribution system, power distribution network that we have, which is exposed all the time to, of course, lightning. And therefore, it needs protection. And this is a major issue in power distribution. The early protection were done by gap. The gap is, the spark gap has a problem that when it strikes, it is a short, which is not very good. On the other hand, a combination of a spark gap plus a varistor, and in the early days it was a silicon carbide, is a very good combination, because number one, the silicon carbide is not exposed all the time to the voltage, and therefore the leakage issue is no issue. And then when it strikes, it's not a short, but really the voltage, there is a clamping voltage here, which sort of very slowly reduces the current. So therefore, this is a much better solution than this one. And finally, there is a tendency today to move toward the zinc oxide varistors, in which they have relatively lower leakage. And I'm showing here some examples from the Siemens. These are stacks of zinc oxide discs so as to sustain very high voltage. And this is the way they are clamped to the structure. So this is the ground side. And here, this is the ground side. And here it is connected to the line. This is just a ceramic support here. So this is the line, a very high line, high voltage line, and then here's the connection. And here they're showing actually a monitoring system. I guess it's for temperature detection and changes in the case of a degradation, severe degradation, then obviously the unit has to be changed. And here is a table. I'm not going all the detail, but it's just to say we are talking about now protection of 145, say in this unit, to 550 kilovolts. We are talking about currents that for striking of 550 amp to 1.2 kiloamp, and of course capability of short time pulses, very high current, 20 kiloamps to 65 kiloamp. And these are just mechanical parameters. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.